3, the datum is at the center. And then from here, based on the examples or countless examples I've done, rule number 5 or 4, the first moment of area cannot cross the centroid. Okay, and then rule number 5, which is very obvious. Okay, when we derive this, when we do this cross section, rule number 5 is the shear flow Q can only flow in one direction only. Okay, so which is similar to liquid flow, right? When you ask what is shear flow, is similar to fluid flow. Okay, now what I'm going to do next is we are going to focus on how to determine the first moment of area. Okay, I'm going to elaborate again. We are going to determine how to find the first moment of area. So I'm going to focus on this cross section over here first. So this is our example. So this example 1, the purpose is to how to select the first moment of area. Okay, how to select the first moment of area. Okay, so now if now we are going to determine, okay, we are going to determine the shear stress at point A and point B. Okay, so we have our Vy coming from the top, right? We have our Vy coming from the top. So very obvious is that we will need to determine our ZZ axis. So I will draw the transformation. This is our Y and this is our Z. We have to focus on our ZZ axis. So we need to find the ZZ, okay? The position of our ZZ. So ZZ axis is also our geometric centroid. Okay, this is our geometric centroid. So when is the case, to find our geometric centroid, very straightforward. You all know this really well. So I will divide this way. This is our flange. This is our left web. And this is our right web. Okay, so if this is our section, this is our flange. And then we have our left web. And then we have our right web. And then we know that if the axis Z of interest, this is our width. And this is our depth. And we are going to take our reference point from the top for our Y bar. So we will have our width and depth. So the width is 160. The depth is 20. Right. So 160 times 20, 3200. Then the other one, our width is 20. And our depth is 100 minus 20 is 80. Okay, it's the same. Width is 20. Depth is 80. 1600. We add all this up. It's 6400. Then from here, we determine our Y bar from the top. Okay, so this is 20 divided by 2, it's 10. From the top, this is 20 plus by 80 divided by 2. Same thing. So this will be 20 plus by 80 divided by 2, 60. And then finally, we have our width, depth, Y bar. So it's 32123. 1600 times 60 is equal to 96,000. 96,000. And then when we add everything up, it's 224. So our global centroid is 224 divided by 6400. Okay, so 224 is equal to 35 millimeters from the top. Right, so from the top, the distance from here to here is 35 millimeters. Okay, that we know so far, and that's what we have found. So if we're going to find the next thing, we're going to determine the shearing stress at point A. Okay, at point A. So this is straightforward at point A, right? So when we sketch our shear flow, right, our shear flow will look like this. Then it will flow here. And then it will flow here. And then this is how a shear flow will look like. Okay. So the shear flow direction will help us determine what is our Q. Okay. So from here, if we look at point A, right, point A is up to this line over here. Okay. So before we go on, this is our centroid. Okay. So this distance to here is 35. Right? And at point A, it stops at the junction between the flange and the web.
I'm sorry, Eugene.
Yes. Hello?
For the flange, shouldn't the shearing the direction, shouldn't it be horizontal, not vertical?
No, I'm not. That is called thin wall analysis. We're not doing thin wall yet.
Oh.
Okay, this is just a standard non-thin wall analysis. Okay. So from here, okay, at point A, the area of interest that we're going to do now is this area now. This is the area of interest. Because point A ends at the flange. If we look at point A, it ends here, right? So that's the area of interest. So when there's the area of interest, we know, right? What we do know now, that over here, This distance over here to here, this is our y bar. And the area stops at here, okay? And that is our y, okay? So that is our y bar, and that is our y, okay? So to calculate our first moment of area, right? So the formula that we're going to use is shear xy at point A is equal to Vy over Izz, right? Qz over T. Okay. So the first thing we have to determine is our Qz is equal to area y bar, and this is equal to width multiplied by depth multiplied by y bar. Okay. So from here, our width is 160, right? So our depth we know is equal to 20 because that's the area of interest. That's 20. So now our y bar is equal to what? Our y bar is equal to 30, right? So sorry, is equal to 35 plus by 20, right? Plus by 20. No, sorry, not plus by 20 because the distance from here to here is 15, right? So 35 plus by 15 multiplied by half. Okay. So this will be equal to 135 plus 15 divided by 2 times by 160 times by 20. So it's equal to 80 times 10 to the power 3 millimeter squared, or sorry, millimeter cube. And this can be equal to 80 times 10 to the power minus 6 meter cube. Okay. So why 35 plus 15? So basically this one I use the formula C plus what? C plus y multiplied by half. C is the maximum distance. The maximum distance is what? 35, right? Y is our 15, and then you just add them together and multiply by half. Okay. So your QZ is equal to AY bar. Now this is the easy part. Now if you look at point A, okay, if you look at point A, right? If we look at point A, which thickness do you take? So if you look at the Q, there is a thickness over here. Do you take this thickness or do you take this thickness? You see where this is coming from, right? So what thickness do you take? So I'll show you both. Okay, I'll show you both. So we have not determined Vy and Izz yet. It's okay because because Vy and Izz are constant. Okay, it's fine. Okay, for now. So if we were to determine at point A, considering T is equal to 0.16 meters, right? So your shear xy at point A will be equal to what? Will be equal to Vy over Izz, right? Then you have 80 times 10 to the power minus 6, and then divide by 0.16. So this will be equal to 80 power minus 6 divided by 0.16 is equal to Vy over Izz, and then multiply by 500 times 10 to the power minus 6. Okay. Or because the thickness, right, at A, you can also consider the what? At the what? At the whack, right? So when that's the case, if we consider A, consider the thickness, okay? So at point A, you have two thickness, okay? You have thickness on the left-hand side thickness of the right hand side, you have twice of 0.02.